Welcome everyone. My name is Scott Levy. I work for Sandia National Laboratories, and I am the session chair for this invited talk session. And before we get started, I want to remind everybody that we're going to do the Q&A in Slack. So you should be able to see in the Zoom chat, there's a link to the Slack channel. And then if you get into the Slack workspace in the general channel, there's also a link to the channel associated with this session. So with that, it is my great pleasure to introduce our invited speaker, Andy Bechtolsheim. So Andy is co-founder and chief architect of Arista Networks. He's responsible for advanced AI, silicon, and optics initiatives. Previously, Andy was a co-founder and chief system architect at Sun, responsible for next generation server storage and network architectures. He received an MS in computer engineering from Carnegie Mellon in 1976 and was a doctoral student in computer engineering at Stanford from 1977 to 1982. He's been honored with a Fulbright Scholarship, the Stanford Entrepreneur Company of the Year Award, the Smithsonian Leadership Award for Innovation, and is a member of the National Academy of Engineering. So with that, I will turn it over to Andy for his talk on why he thinks the answer to the question, can interconnects keep up with AI, is yes. So Andy, it is all yours.
Hi, can you see my slides?
Yes.
Okay, so to jump right in, I want to talk about expectations on XPU performance and I/O scaling, which realistically is a factor of 100 over the next few years, and how to connect these XPUs within a cluster together, and how to minimize overall interconnect power consumption. Now, jumping right into the TSMC roadmap here, going from 5 nanometer, which is sort of last year's technology, to 3 nanometer to 2 nanometer, does provide a non-trivial amount of improvement in chip density, power efficiency, and what I would call the density times speed product in the same area, basically a factor of 2, going from 5 nanometer to 2 nanometer. So, and that's at the same power, right? So if we design chips in the same size in 2 nanometer, we would expect to get twice the throughput, which is obviously far away from a factor of 100. However, the real gain is larger substrates. The COWS technology is scaling from 3.3 times radical size last year to 5.5 times and maybe even 8 times. And then TSMC is developing the system silicon on wafer technology, which basically takes a whole 12-inch wafer, 8 by 8 inch substrate to plot down as many GPUs and HBM memories as you can fit. So the increase with that higher density packaging is tremendous, because basically between the underlying silicon technology, the substrate technology, and architecture improvements, there's a clear shot at a 50-fold improvement in performance compared to 2022. And with better cooling, one could probably get another factor of 2 for an aggregate of 100x in this time frame. Now, this, of course, will require a lot more I/O, and I try to normalize this here to 800 gig ports, unidirectional per chip, where a few years ago there was maybe 3.2 terabits of I/O. This combines both scale up and scale out bandwidth, right? And current chips have double of that, and the next ones will have double of that, and the next ones will have double of that. But it's a fairly predictable path from where we are today to 12.8 going to 25.6 T per chip. And again, these are unidirectional numbers. Some vendors quote bidirectional numbers, which are twice as large, but at least in networking, people always refer to the unidirectional performance. Now, if we convert this to the I/O power, and I'm talking about high-speed SerDes I/O power with next-generation SerDes, the current one's a little higher, but normalizing this down to about 4 picojoule per bit on the SerDes I/O, yeah, it does take some power to get the I/O off the chip, but it is actually far less than is commonly assumed, for the simple reason that the CPU or XPU power is going up dramatically as well. So the current chips are around 1,000 watts, the next ones will be 2,000 watts, the ones after that will be 4,000 watts, which is not a problem from a cooling perspective, because the area on the chip on the substrate goes up. So the thermal density per square millimeter, the heat flux, is actually not really increasing. However, the total power per substrate goes up, and so does the I/O, but the I/O power, at least in my calculation here, stays at around 2.5%, which is arguably not significant. Now, on the scaling the I/O bandwidth with larger substrates, same thing. As the substrate goes up, we get much more beachfront to provide much more I/O than ever. So assuming a terabit per millimeter beachfront for high-speed SerDes today, on a single chip with 25 by 25 millimeter, that's 100 terabits. With a larger substrate chip that's 50 by 50, that's 200 terabits. And for an even bigger one, 100 by 100 millimeter multi-chip substrate, that would be 400 terabits. That's with 200 gig SerDes technology, and potentially would double to 800 terabits with 400 gig. So none of these are limitations. And what it all comes down to is, yeah, it is much lower power to go die to die on the substrate, depending on how close these things are together. It could be 0.2, 0.3, 0.4 picojoules per bit. And because you can stack the rows, you can get 5 to 10 terabits per millimeter. Off chip is harder because you're driving more distance and you need more power and more drivers to do that. But it seems feasible to get beyond the terabit to perhaps even 2 terabits per bit. So none of this is actually a limitation. Now, and I want to highlight here the role of the high-speed SerDes as the common interface. I call this the universal electrical interface to support any mixture of either copper cables, AOC cables, or any type of optics modules. And there's a clear roadmap here from the 112 gig today, shipping today, to the 224 that's around the corner, and 448 in the future. And there's a matching optics module roadmap going from 800 gig modules today to 600 gig and 3200 for an 8-lane optics. So there really isn't anything in this picture that requires changes. And as you all know, and was discussed over the last day, within the rack, passive copper is very compelling. It's very low cost, very low power, very high reliability. And it is also true that one can increase the density of these liquid-cooled racks to much, much higher power levels. The current generation is around 120 kilowatts and has 64 or 72 GPUs. The next one will be at least double, if not quadruple that number. Obviously, the power will go up correspondingly. People are designing 400, even 500 kilowatt liquid-cooled racks. But the benefit is you can address the interconnectivity within that rack with copper cable, which again is the lowest cost and the lowest power. Now, the challenge is ultimately beyond the rack, how to tie together multiple racks in rows and data centers. And yes, there is a penalty in cost, power, and reliability for doing that. And the question ultimately comes down to how to minimize that penalty and and this, I believe, comes down to linear optics. And there's also separately great interest in optimizing for short links in the range of, say, 10 or 15 meters for the AI clusters that require that kind of distance. So the rest of my talk, I want to focus on those issues. So starting with the SerDes migration, again, what's shipping today, at least on the networking side, is primarily 110, 112 gig PAM4. This will transition to 224 gig over the next 2 years. And arguably, this will be one of the fastest transitions in the history of Ethernet, for the simple reason that 600 gig or 224 gig SerDes have many advantages, most importantly, cost. When you compare 800 gig modules, optics modules, to future 600 gig optics modules, and you open them up, they will look identical. The only difference is one runs at twice the speed per lane. But the number of lasers, the number of detectors, fibers, connectors is all the same. There is one big problem here, which is power. So the early prototypes of 600 gig DR8 optics, which have a DSP, come in at, you won't believe this, at close to 30 watts, which is actually higher picojoule per bit than the latest 800 gig optics, which with a DSP are around 13 watts. The LR optics haven't been built yet, but based on sort of back of the envelope calculation, there will be around 20 watts. And the LPO modules are still in development as well. And hopefully we'll see those around 10 watts. So there's a tremendous power reduction from LPO to LRO to DSP optics. And this multiplies, translating this to picojoules. So if you compare GPU with a 224 gig PAM4 LR SerDes, and that power is allocated to the GPU, of what the incremental power is for the interconnect. A copper cable would be 0 picojoule per bit, the LPO optics would be 6, LRO 12, and DSP optics 18 picojoules per bit. This is using the raw data rate as the conversion for the picojoule per bit number. Now, at the scale of a 100K node cluster, these numbers become very, very large. Assuming for a second the 2028 GPU with 25.6 terabits unidirectional I/O, which is the equivalent of 16 600 gig optics. And then let's also assume a two-level fabric, which allows for a non-blocking interconnect for this whole cluster. Maybe this is overkill, but let's just assume this as the worst case design or the most aggressive design. The two-level tier cluster requires 4 optics for each connection. So with 100K optics and 16K ports per GPU and 4, there would be 6.4 million 600 gig optics just for this 100K nodes. And remember, some people want to build a million GPU clusters. But the interesting part here is the GPU power relative to the optics power. So assuming a rounded up number of 4 kilowatts per GPU, and this excluding the optics power, for the 100,000 GPUs, the optics power on top of that would be almost 200 megawatts for DSP optics and 64 megawatts for LPO optics. Needless to say, nobody would deploy DSP-based optics for this application because you can't afford it. So we need linear optics, and how do we get there? Well, basically, it's whether you call these things linear pluggable optics or near-word pluggable optics or co-packaged optics, they are all linear interfaces. In other words, none of these optics have an additional DSP retimer to retime the signal between the SerDes on the switch chip and the optical channel. And as a consequence, all of these optics have basically very similar power consumption. The only difference is that with pluggable optics, the electrical channel has a somewhat higher loss, and you need a somewhat higher driver power to compensate for that. And on the near-packaged and co-packaged optics, which tend to use external light sources or pluggable lasers for reliability reasons, you have a higher optical loss in those optical connections, and that requires higher optical power. But bottom line, at the device level, the power consumption of these devices is very, very similar. Now, starting with co-packaged optics, this is not a new idea. Co-packaged optics have been around since for a long time, but the one system that really sticks out in my mind as a classical example of implementing this at scale was the IBM Power 775 Blue Gene supercomputer, which used the Avago, which is today Broadcom micropods, which were 12 channels of VCSELs per module, and they were soldered down next to the GPU or their Blue Gene chips, the power chips. And there was a whole bunch of them on a MLC type module, and all interconnected with multi-mode fiber. And surprisingly, this worked, at scale with I don't know, 10,000s of these optics per system. And as far as I know, this is still the highest volume of co-packaged optics ever shipped. There have been many other demonstrations since then over the years, but none of them were able to get to volume production. And the fundamental problems of the technology, which have to do with manufacturability and serviceability, haven't really changed. But the more important issue is that CPU is not required to solve the problem, so why add other problems on the to-do list? Near-packaged optics separate the optics from the physical GPU, XPU switch device and connects it with a fairly short electrical channel. And this does allow repairability, maybe not in the field, but certainly at the factory, which still requires, unfortunately, a switch replacement operation if something fails, but at least one can repair this in a reasonable fashion. This was tried for many years as part of the COBO consortium. This is a picture here that developed different styles of modules for 16 channels and 32 channels and different power levels, but none of this got any traction because pluggable optics solved essentially the same issues. Which leads me to linear pluggable optics, which compared to their DSP variety have lower power, lower latency, lower cost, and higher reliability. and do not create any of the manufacturability or serviceability issues of the CPU or NPU optics. As you know, there is a MSA that was formed to build a multi-vendor ecosystem around this with leading system, module, and service vendors. The MSA has been focused on the 112 gig spec, which will be published before ECOG in a few weeks. There's ongoing multi-vendor interoperability testing to enable multiple suppliers to predictably work together. And the supply chain is ready and able to ramp these products to volume next year. And I can say with a good service, the channel just works. Now, the real question at this point is actually LPO at 224 gig PAM4, which has the same principles, but needs a very, very clean, low-loss electrical channel between the switch and the optics module, ideally no higher than 15 dB. And this most likely will require flywheel cables, which reduce channel loss and channel impairments. They will also require high-performance TIAs and linear drivers, some of which are still being designed. But based on simulation work, it will work. On the other hand, we will not for sure until we actually build these systems. I can say that for a NIC or an XPU application, the much shorter electrical channel makes an LPO a no-brainer choice. For a switch with longer electrical lanes, it is more challenging, but it does look doable with flywheel cables. And obviously, there will be a lot of testing going on between now and the next OFC trade show in 2025 to report on that. This is an example of flywheel cables from the NVLink switch that sits in an NVIDIA rack. And you can see the copper cables that go from a connector very close to the switch chip to the backplane, which is then cabled to the GPUs, where there's a similar short cable as well. Now, talking about flywheel cables, there's one technology I wanted to highlight here, which has to do with, some people call this co-packaged copper. The idea is that you terminate the Twin-X cables directly on the substrate package, on the organic substrate for the switch chip. And surprisingly, one can get 512 channels, which is 1024 diff pairs, directly terminated on a 110 by 110 millimeter substrate, as shown by the company Luxshare, which is promoting this type of technology. I can say that you will not get a better electrical channel than this. These can go directly to an OSFP plug on the front panel. And the ongoing testing indicates that this will also work at 448 gig PAM4 or PAM6. So there's at least a path to even higher speed SerDes I/O in the future with co-packaged copper. Now, there are some trade-offs on the 448 side. In particular, PAM6, which is a much lower Nyquist frequency, is much easier on copper than PAM4, which is 112 gig. And there is, of course, the other side of this, which for optics, PAM4 works much better than PAM6. You get much better SNR. So the difficult situation here is you really don't want a DSP gearbox that converts from PAM6 on the electrical side to PAM4 on the optical side, because that, again, would burn a lot of power. So I think the challenge is on to try to get the entire channel to work in PAM4, which, again, on the electrical side, will require ultra-short reach connections. And this may be the time where co-packaging becomes more relevant, because you do need the closest or the shortest electrical channel. Also on the optics side, high bandwidth modulators are the key. Thin film Lyobate will be there for sure. EML may have a shot to get there. Silicon photonics, I'm not so sure, but there's work to be done. And there's also some time. We expect to see 448 gig SerDes in the 26-27 timeframe. And I'm doubling the slide here. But summarizing this, the future for optics is linear, and it doesn't matter whether it's LPO, NPO, or CPO. The LPO is just by far the easiest technology to deploy for customers. It allows field replacements for individual optics, and unfortunately, optics are still not as reliable as we wish they would be. NPO and CPO require switch replacement in the case of an optics failure, and that's, of course, much more difficult. So I now want to spend a couple of slides to talk about the chicken egg problem with new optics technologies, and in particular, the kind of things we heard yesterday, which are, one could summarize them as slow and wide or slower and wider, which do have benefits, right? You do get a lower power, less picojoules per bit when you go down to 32 gig NRC, or in the case of micro LEDs to 4 gigabits per channel. And you also get better bit error rates, with NRC coatings and so on. The question is how to get these new technologies into the market, because realistically today they require inverse gearboxes, which unfortunately negates the potential power saving. And if one co-package them, it creates this chicken egg problem that have to do with high volume manufacturing. But focusing on the inverse gearbox for a second, so if we take the Avicenna micro LEDs that we heard about yesterday, which I believe are around 1 or 1.25 picojoule per bit, including the driver and the TAA on the optics side. But that's again at roughly 4 gigabits. To connect them to a 224 gig channel, one needs an inverse gearbox. And unfortunately, the SerDes power to connect to that channel and the gearbox function is 3 times higher than the optics, which is kind of a shame. So at the end of the day, it's still at least 5 picojoules per bit, but it does offer, some of the other advantages of the technology, including having spare lanes and so on. With 32 gig NRZ, it's kind of the same picture. So silicon photonics micro rings and single mode lasers are somewhat higher power than the micro LEDs, but again, it needs an inverse gearbox, which is roughly the same cost as the other one. So this one comes in at around 6.5 picojoule per bit based on the back of the envelope calculation, which is unfortunately no better than a standard LPO design. So the problem here is that, new technologies that are promising are great, but how to get them to volume production, because you cannot sort of commit a XPU design to rely on a technology that's not proven, because that could be a very, very costly mistake, right? And at the same time, until a volume is in high volume production, it's not proven to begin with. So my sense is these technologies will not get adopted at the high volume level unless they're really required to solve a significant problem. And the easiest way to adopt them is actually with pluggable modules, because then one can decouple the timeline for the XPUs and the switches from the timeline on the underlying optics development, and one can plug them in by the time they are mature. So I do believe that pluggable optics modules have the ability to enable new optics technologies, whether they are micro LEDs or other slow and wide type of technologies. But every alternative is basically very, very difficult. And the issue is that adding additional risks to the XPU schedule, which already is taking all the risk on the world on new process technology and new SOWS substrate sizes and so on, it's just not a rational decision to make. So the low risk decision is to keep going with high-speed SerDes, coming off these latest and greatest XPUs and switches, and then align the optics either close by to these packages or with copper cables or with pluggable modules to be as closely to minimize the electrical losses and to have a way to plug them into the shipping products. Bottom line is, market success is all about time to market, and nobody's going to wait for technology that's actually not available to ship in volume. And the best way to get there is with pluggable modules. So I think that's my last slide here. I'm happy to take any kind of questions.
Great. Thank you, Andy. That was a really interesting talk. Let's see. Got a couple of questions in the chat or in Slack. So if anybody else has questions, please post them. Let's see, the first one is in a recent Optical webinar, Meta presented on the lack of diagnostics and telemetry for LPO being a major issue. How will this be addressed with no DSP?
Yeah, that's a very good point. So the visibility of different test points along the channel is, of course, paramount to be able to diagnose or to even validate the optics, right? And um, what people are doing now is they're designing what they call smart drivers, which basically are still a linear driver, but they allow you to read out the signal coming in and the quality of the signal as part of their design, which does not add a significant amount of power, but it's more than a conventional driver that just amplifies the signal. So yes, we will need additional test points at every path in the way. Sorry, I can't hear you.
I'll try unmuting and see if that helps.
Yes, that works.
Okay. Uh, we got another question here. How might LPO scale for 448G?
Well, again, if 448 were to require DSPs, it is kind of a non-starter because the power is just too high, right? So the electrical channel has to be, the numbers don't actually change. It's just the losses go up tremendously. They almost double, every time you double the baud rates. So let's say in a 112 gig environment, you could have a 12-inch PC board to have a 10 dB loss channel on the board, not counting the package loss, right, on the module and the BGA. For 224, you have to either have flywire cables or a much shorter electrical channel to make that same number work. At 448, you barely get off the package, electrically speaking. So yes, we will need to densify the packaging to bring the optics closer to the chip. But my belief is you can still do this with pluggable optics. So I don't know the fascination where people think they have to solder these things down.
Okay. Let's see. And I think the only other question we have, it looks like was answered. It's about on the use of LEDs. The application was XPU, and it says this was the Avicena solution, and you addressed it. So I think we can.
Yeah, I mean, the point is, yes, the lowest power is to integrate micro LEDs on the BGA package, right? It's just that only works if it works. And the question is, when can you actually make the decision in a way that you don't risk your entire program? Because otherwise you're spending 2 years to optimize that solution and then you can ship it. That doesn't do anybody any good. So it needs disaggregation, at least for now, until these new technologies are proven to be producible in the millions of units.
And then I think, let's see, we got one more. What does the roadmap look like for CPO and LPO?
Well, on the LPO side, today, it's the pluggable module roadmap. The form factor is basically at this point OSFP, and there are people who are going to make this work at 448 gig, at least with PAM4, PAM6, sorry, electrical. With PAM4, it's more challenging. So we may need a new connector, and it takes time, even to develop a new pluggable form factor, right? It takes a multi-vendor effort to get that right. So we may need to develop new pluggables that can handle the 448 gig PAM4, for example. But for now, the 600 gig OSFP, which is 8 by 200, and the OSFP XD, which is 16 channels, are well established and they will perform well.
Okay. I think that does it for the questions we have, and we're coming up to the lunch break. So I'd like to thank you very much again for a really interesting and engaging presentation. And we'll turn it over to the lunch break. And thank you again, Andy. This was really,
My
really
pleasure.
valuable. Yep.
Okay, bye-bye.